Right, and let's take a look at sections 13.2 and 13.3, which covers some calculus on vector functions, which means we're going to be looking at integrals and derivatives of vector valued functions. So just the one learning objective this time. That's to work with that derivative and integral. So a couple of those definitions. If we have some vector function r, where r, g, and h are differentiable, then the derivative of our vector valued function r is just the vector that contains the derivatives of each of our components, f, g, and h, in their same places. Whereas if f, g, and h are integrable, so again, same components, same r, then the definite integral of r, which means that we're integrating from a to b, is just the integral of each component from a to b in its place. So if we just take a look at an example of how that's going to go, finding a derivative for r prime of t means that it still comes out to be a vector, but we just take, instead of one derivative like we would have in Calc 1, it's Calc 3, so now we take 3 derivatives. So 3t squared for the x component. This looks like cosine t and positive cosine t for the y component, and 3e to the 3t for the z component. And then if we want to evaluate the definite integral of our function r, then we just need to integrate each piece. So we're looking at t cubed, which should integrate to t to the 4th over 4. We'll look at the integral of sine, which this time should come out to negative cosine of t. We're integrating, there's a negative on the sine integral, and e to the 3t integrates to 1/3 e to the 3t. And then we need to evaluate that. So these vector valued pieces from 0 to pi, since that's what we're asked to integrate this time. So I'm being a little shorthanded with the notation. Technically, I should have a bar where I'm evaluating from 0 to pi 3 different times, one on each component. But for simplicity's sake, I'm just writing it once at the end of the vector, and then I'll evaluate each piece from 0 to pi, which means that we are looking at pi to the 4th power over 4 for that x component. For that y component, cosine of pi is -1. So I'll be looking at -1, which comes out to +1. So let's maybe do that. -1. Minus a negative cosine of 0, which is +1. And finally, evaluating that last thing from 0 to pi, I'll have 1/3 e to the 3 pi minus 1/3 e to the 0, so minus 1/3 times 1. If we plug that in, and then we'll close off that vector. I'll inch it a little bit over to the right so it's not off the page. And then we can simplify this a little bit. So our first piece, pi to the 4th power over 4. Our second piece, the y component is 2. And onto that third piece, 1/3 times e to the 3 pi minus 1. Might be the simplest way to write that one out. And that would be the value of the definite integral. So again, It's just the same way that we would evaluate a definite integral in Calc 1. We're just doing it 3 times. All right, and then out of the textbook, a few different properties of derivatives of vector valued functions. So u and v are both going to be differentiable vector functions. C is a scalar, and f is a real valued function, which means that f is not a vector function. So f is just a function like what we're used to seeing. And we have much the same rules that show up. The top is just the sum rule for vector functions. If we have a constant being multiplied in, we can just not worry about the constant and take the derivative of the vector valued function, multiply the constant at the end. So rule 2. Rule 3 is, well, rule 3, 4, and 5 are all basically the product rule. It's just we'll look at 3 different types of products when we're looking at vector valued functions. So we have a product of a scalar function and a vector function, which works just the way the product rule says it would. We also have a product that is the dot product of 2 functions, and that'll also work out quite similarly. And then also the cross product was the third sort of product we had for vector functions. And again, each one works out to be much the same. We just take derivatives of the component functions one at a time. Unless that we also have a chain rule, which works pretty much just the same way that it would back in Calc 1. So if we wanted to put one of those into practice, so assume that we know f of 1 is 3, f prime of 1 is -4. We know what u of t is and u prime of t. Then we want to find the derivative of this thing when t is equal to 1. I just realized that there's a slight error in the setup of this problem. So since u should be a vector valued function, if it were just a constant vector and we took its derivative, we would definitely get the 0 derivative. So this is supposed to say that u of 1, u of 1, yeah, let's scribble that out, u of 1, this should have been u prime of 1. There we go, and then now this all works out. So looks like we're going to want to use the product rule for a scalar function being multiplied into a vector function. So we're going to look at property 3, which says that this derivative should come out to, well, just the product rule, sort of like we're used to seeing it. So we'll have f prime of 1 times u of 1, where u is that vector value, plus f of 1 times u prime of 1, which should look like -4 times the vector 3, 0, -5, plus f of 1, which is 3, times the vector value u prime of 1, which is 0, 1, 2. And then this just becomes the sum of 2 vectors. So we look at that x component. I'll have -4 times 3 plus 3 times 0, which is -12. The y component, -4 times 0 plus 3 times 1, which is 3. And the z component, -4 times -5 plus 3 times 2 will be +20 plus 6, so 26. And there we have it. All right, then we'll also want to look at arc length, which is now moving into the 13.3 section. So the definition at the top is just a reminder of the distance between 2 points, or the distance formula. It's the square root of each of the x, y, and z distances squared. And we're going to use that idea to lightly construct into the theorem for arc length. So if C is some curve given by the vector function R, sometimes we'll just call it x, y, and z, each a function of t for simplicity's sake. For t being in between a and b, which will be the limits of this curve, or the endpoints of this curve, then the length of that curve C will be given by the equation below, where it's the integral of the magnitude of r prime and integrated from a to b, which if we expand on that ends up looking quite a lot like the distance formula, since the magnitude of r prime would be just the square root of x prime squared plus y prime squared plus z prime squared. Since x prime, y prime, and z prime each make up the components of r prime. And ultimately what this ends up looking like is the sum of a bunch of infinitesimal straight line distances, where we'll just take the limit as those distances come to zero, so that we have an infinite number of them, and add them all up. So if we take a look at figure 1 to just kind of give us kind of the motivation for where this theorem is coming from, I've got my curve in blue, and then several straight lines in magenta as I hop from point to point. And if I did an infinite number of really, really small magenta lines and added them all up, I would get the length of that curve. And that's basically what our curve is here. So if we then bring that into an example, we're going to look to find the arc length of a vector function, r of t, which is cosine t, sine t, and 2t, and we'll integrate from 0 to 5. So step 1 is probably going to be to get r prime of t, since we'll need the magnitude of it, or at least we'll need x prime, y prime, and z prime. So if we put all those together, derivative of cosine is going to be negative sine. The derivative of sine will be positive cosine. And the derivative of 2t is 2. So then our arc length, or the length of our curve C, should be the integral from 0 to 5 of the square root of negative sine t squared plus cosine t squared plus 2 squared. Don't forget your dt. Let's do it in green, dt. And our goal is going to be to just integrate this thing. So a trig identity is going to help us out here quite a bit. That particular identity is sine squared plus cosine squared is equal to 1 as long as it's the same input for both sine and cosine. And that's exactly what we have here. We'll have sine squared plus cosine squared. So that part will be just 1, meaning that we're looking at the integral from 0 to 5 of the square root of 1 plus 4. 1 plus 4. Where 1 is coming from those two pieces added up. Still dt. Now our function doesn't depend on t at all, it's just the square root of 5. So if we integrate that thing from 0 to 5, we should get 5 times the square root of 5.